With each captivating picture caught by the James Webb Space Telescope, it continues to assemble examinations from different corners of the universe, including planets inside our own planetary framework. A year sooner, we pondered our most critical brief ocean pictures showing the Kina Cloud, the Stephan Quintet, and moreover, strikingly, the charming profound field picture. This express picture obviously portrays various systems resting in the immense degree of the universe, satisfying the questions made. The James Webb Space Telescope hasn't quit being a labyrinth. It has, as a matter of fact, uncovered objects that test profoundly grounded cosmological speculation. These surprising discoveries are currently being named universe breakers by cosmologists, disappointing laid-out specialists with their capacity to challenge existing hypotheses. The purposes behind these revelations remain covered in secret, tossing our hypotheses and theories into confusion. So, what's the most recent scoop from the James Webb Space Telescope? What wonderful new disclosures has it uncovered that were previously obscure to us? Join us as we plunge into the discoveries of how the James Webb Telescope has introduced proof proposing the presence of another universe, testing the standard comprehension of the Big Bang. Our universe, as we've long realized, rose from a more sultry, denser state through a hypothesis known as the hot Big Bang. This thought, a critical logical accomplishment over the course of the last century, acquired overpowering help during the 1960s with the discovery of the cosmic microwave background, CMB, a reverberation from the early hot and thick state. Over the long haul, the Big Bang has stayed the triumphant hypothesis, making sense of the origins of our universe. Everything considered, new and basic insights have driven cosmologists and astrophysicists to rethink both the continuous extension and the Big Bang itself. In spite of these difficulties, elective speculations have neglected to get momentum, with a common hypothesis of the universe's starting point persevering. As per the predominant view, the universe began as a more modest, denser universe in the far-off past. The presence of radiation, for example, photons, shows that the universe was more sultry at its start and has since cooled. Extrapolating backward in time, the thickness, temperature, and energy levels fluctuated where a peculiarity could shape, and the laws of physical science would break down around 10 superscript 3 seconds. In such a limited capacity to focus time, minuscule distances, brief time frame scales, and high energy levels challenge our comprehension. Rewinding the infinite clock to the speculative 0 point. If the universe began as hot and thick, it would have expanded and cooled, delivering tremendous measures of particles and antiparticles, with abundance particles being obliterated by radiation as temperatures diminished. The breakdown of the electroweak and Higgs powers prompted the development of the 4 key forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles called quarks and gluons. The blend of protons and neutrons prompted the arrangement of light cores, for example, deuterium, helium-3, helium-4, and lithium-7. Overdense regions experienced development because of radiation pressure, followed by gravitational breakdown, prompting the arrangement of enormous-scale structures. Around 380,000 years after the fact, the discovery of the cosmic microwave background laid out the hypothesis of the Big Bang as the most supported explanation for the universe's creation, portraying the early universe as a hot, thick soup of subatomic particles slowly cooling over time. HDH banter, Big Bang versus steady-state hypothesis. While most cosmologists and astrophysicists embrace the Big Bang theory, firm defenders of the steady-state hypothesis, such as Fred Hoyle, continued to support increasingly doubtful ideas, only to face defeat despite overwhelming evidence. The proof presented was decisive. It wasn't darkening starlight or reflected heat from dust. The celestial glow showed remarkable consistency, resembling a perfect black body, but had no association with known objects in the universe. Despite this, Hoyle and his colleagues continued to undermine scientific progress by backing scientifically questionable ideas. Meanwhile, the fields of space science and cosmology underwent massive changes from the 1960s through the 2000s, with cosmology making particularly significant strides. We mapped the universe, described its large-scale structure, and analyzed the growth, evolution, and dynamic interactions of galaxies and their stellar populations. Yet, even with these advances, we encountered anomalies that challenged explanations within the framework of the Big Bang Theory. Most notably, the absence of predicted relics, such as magnetic monopoles or particles from grand unification, led many to reconsider parts of the theory. The universe we observe today seems to require forces beyond our current understanding. Despite these challenges, the expansionary model and its difficulties persist, while existing theories fail to account for observed abnormalities. Two approaches have emerged: refine current theories or consider alternative explanations. The theory of inflation has emerged as the most promising framework for extending the Big Bang perspective. Inflation suggests a brief period of rapid expansion that smoothed the universe, giving it uniform properties. It addresses the horizon problem and predicts the development of quantum fluctuations, which manifest as density and temperature variations. The predictions of inflation align with observed patterns and changes, reinforcing its validity. However, despite alternative theories, inflation's scientific strength remains unparalleled. Roger Penrose's work, alongside his collaboration with Stephen Hawking, failed to match the progress of inflation in explaining the earliest moments of the universe. Recently, efforts have been made to undermine the authenticity of the inflation theory by supporting conformal cyclic cosmology. However, this theory is inherently flawed from a scientific perspective. The key distinction lies in their predictions. Conformal cyclic cosmology suggests that remnants from a universe preceding the Big Bang are imprinted in the cosmic microwave background and the large-scale structure of the universe. Conversely, inflationary theory maintains that the end of inflation and the hot Big Bang are causally disconnected from any pre-Big Bang time. James Webb Telescope's astonishing revelations. Astronomers quickly noticed peculiarities in the images sent by the James Webb Space Telescope starting in 2022. These discoveries could require a reassessment of key aspects of the universe's origins and development. One significant revelation made by the Webb telescope was the presence of fully developed galaxies much earlier than expected by the standard cosmological model. This inconsistency challenges the established sequence of events following the Big Bang, where stars and black holes form first, followed by galaxies. Such discoveries disrupt our understanding, like encountering grandparents portrayed as children in a story. Moreover, later evidence has revealed anomalies within major theories of the universe, such as a persistent error in determining the Hubble constant, which continues despite improvements in data accuracy and measurement methods. New data from the Webb telescope presents challenges to the current cosmological model. These issues highlight flaws within the model, raising questions among researchers and physicists. While the model has undergone changes recently to align with emerging data, some argue that these adjustments have been too accommodating. Thus, there is growing recognition that a change in perspective may be necessary, possibly reshaping our understanding of the universe's fundamental properties. The standard model of cosmology, hailed as a triumph of human knowledge, emerged from Edwin Hubble's groundbreaking discovery of the expanding universe during the 1920s. Subsequent discoveries, such as the detection of cosmic microwave background radiation in 1964, confirmed the theory of the universe's origin as the most plausible explanation. Reconsidering cosmology. Achieving the current level of precision in cosmological understanding has required theoretical extrapolation beyond observational data. The possibility of boundless expansion, introduced in 1981, was proposed to resolve inconsistencies in earlier Big Bang models, further emphasizing the dynamic nature of cosmological theory. According to this model, the early universe underwent rapid exponential expansion shortly after the Big Bang. While specific problems are addressed by this theory, new challenges arise, especially given the prevailing belief in the existence of a single universe. Perhaps there are countless others beyond our observational reach. Some observable phenomena, such as singularities within black holes, gain support through indirect evidence. However, the startling revelations of the Webb Space Telescope regarding the evolution of galaxies and the ongoing issues with the Hubble constant rays concerns that we may be approaching a tipping point where a major revision of our current cosmological model becomes essential. This could require a complete reassessment of the fundamental building blocks of the universe, including the very nature of existence itself. Cosmology, unlike many other scientific fields, deals with fundamental questions about the universe, its origins, and our place within it. The exploration of consciousness in quantum physics also investigates similar subjects, examining the intersection of theory and reality. It is crucial to examine these foundational assumptions, given the impact of theoretical expectations on data collection. History has shown that shifts in scientific thought, such as the transition from geocentrism to heliocentrism, or the discoveries of evolution and relativity, have redefined our understanding of the universe. Perhaps we are on the brink of another such transformation in our understanding of the cosmos, exploring the limits of cosmological theories. As our understanding of the universe deepens, cosmological models must evolve to incorporate new discoveries. The James Webb Space Telescope, JWST, has already challenged long-standing assumptions by revealing galaxies that seem too developed for their age according to the Big Bang timeline. These unexpected findings suggest that key aspects of cosmic evolution may be misunderstood or incomplete. Additionally, unresolved issues like the Hubble constant discrepancy continue to puzzle scientists. Different methods of measuring the universe's expansion rate yield conflicting results, casting doubt on our grasp of the cosmos' underlying mechanics. Despite improved precision in measurements, the gap remains stubbornly wide, hinting at unknown factors influencing cosmic expansion. The discovery of early, massive galaxies and the persistence of the Hubble constant anomaly suggest that current models might need significant revisions. Some researchers propose that dark matter and dark energy, which make up most of the universe's mass energy content, might behave differently than previously thought. Others suggest entirely new physics could be at play. Alternative theories and future prospects. Given the growing body of puzzling evidence, some scientists are revisiting alternative cosmological theories. Among these are 1. Modified gravity theories. These suggest that gravity itself might operate differently on cosmic scales, which could explain unexpected galactic dynamics without invoking dark matter. 2. Multiverse hypotheses. If multiple universes exist beyond our observable cosmos, their interactions might influence our universe's evolution in unpredictable ways. 3. Quantum cosmology. This approach explores how quantum mechanics might govern the universe's birth and development, potentially redefining the concept of time and space. Despite these speculative ideas, the standard model of cosmology, anchored in the Big Bang and cosmic inflation theories, remains dominant due to its strong predictive power. However, as the JWST continues its mission, its data could either strengthen the current model or push science toward a revolutionary new framework. The future of cosmic exploration. The James Webb Space Telescope represents just the beginning of a new era in cosmic exploration. Upcoming missions, such as the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission, aim to investigate dark energy and the universe's large-scale structure in greater detail. These projects could provide crucial insights into cosmic expansion, galactic formation, and the origins of dark matter. Moreover, advances in ground-based observatories, such as the extremely large telescope YELTI and the Square Kilometer Array SK, promise unprecedented observational capabilities. These cutting-edge facilities will complement space telescopes by conducting deeper surveys of the cosmos and detecting faint signals from distant galaxies, revolutionizing our understanding of the universe. The universe's story may be far more complex than previously imagined. The combination of new observational technologies, theoretical breakthroughs, and computational advancements could fundamentally reshape our understanding of cosmic origins. What lies beyond the observable universe may be far stranger and more fascinating than anything envisioned by current cosmological models. As history has shown, scientific revolutions often arise when persistent anomalies challenge established theories. Perhaps the revelations from the James Webb Space Telescope and future observatories will mark the beginning of such a transformative era, one that could redefine humanity's place in the universe and unlock the secrets of existence itself.